We have successfully completed the theoretical explanation regarding the usage of the millis function in Arduino programming. This important function allows us to perform time-based operations without pausing the program, making it a crucial concept for efficient project development. Now, we will move on to a practical application where we will control the blinking of 5 individual LEDs, each blinking at different time intervals. This project is specifically designed to help us better understand how the millis function can be used for such operations. We will perform our practical application using the circuit currently displayed on the screen. The circuit can be built and tested either using the Tinkercad simulation platform or by assembling it in a physical environment with real components. You can observe a time-lapsed video showcasing the physical assembly of the circuit, giving you a clearer idea of how the components are connected. In this application, instead of using the delay function, we will utilize the millis function to manage time-based operations. Each of the LEDs will blink at specific time intervals measured in milliseconds, which will demonstrate the precise timing capabilities of the millis function. We will ensure that all 5 LEDs operate independently of each other, each with its unique blinking interval, without any interference between them. It is worth noting that the LEDs in this project could just as easily be replaced with motors or other electronic components, which can also be controlled independently using the millis function. So this method allows us to independently control any circuit component, such as sensors, motors, or buzzers, using the millis function, demonstrating its versatility in various applications. Now, let us proceed to the coding phase of our project, where we will write and upload the program that controls the LEDs. At the very beginning of the program, we will define variables and constants above the setup and loop blocks. The const keyword ensures that these values cannot be changed later in the program. This makes the code more reliable and prevents accidental errors. The byte data type is used because it efficiently stores small numbers between 0 and 255. Since Arduino pins are small integers, this is an excellent choice to save memory. Now, we are assigning specific Arduino pin numbers to represent different colored LEDs. White LED is connected to pin 2, yellow LED to pin 3, red LED to pin 4, green LED to pin 5, and blue LED to pin 6. This structure makes it easy to understand which pin controls which LED. Then, we will declare variables to track the timing of each LED and the delays between their state changes. The unsigned long type is chosen because millis function returns the number of milliseconds since the program started, which can be a large value. We initialize a variable to store the current time in milliseconds, which will later be updated and used to track elapsed time for controlling time-dependent operations like toggling LEDs, and we set its value 0 to ensure that the current time is initialized with a default value to avoid potential errors from uninitialized variables before it is updated with the actual time. Each LED has its own delay value, controlling how frequently it turns on and off. After powering the Arduino board, we need variables to store the specific timestamps in milliseconds when each LED turns on and off. These variables track the moments of state changes for each LED. Without them, it would be impossible to ensure that the millis function allows each LED to blink independently at its unique time intervals without interfering with one another. Now, we are defining the variables necessary to track the state change timings for each LED. Here, unsigned long is necessary because the millis function returns large values in milliseconds as the program runs, which can exceed the limit of smaller data types like integer. The white time variable is used to store the last recorded time for the white LED state changes, and we set its value to 0. Similarly, yellow time, red time, green time, and blue time serve the same purpose for the yellow, red, green, and blue LEDs, respectively. These variables are all set to 0 initially to ensure a clear starting point before they are updated during the program's execution. This allows the program to calculate elapsed time for each LED independently, enabling precise control of their on or off toggling based on their specific delay intervals. Now, we will define the time interval in milliseconds for the LEDs to blink on and off. Each LED has its own delay value, controlling how frequently it turns on and off. The white LED toggles every 2000 milliseconds, the yellow LED every 1000 milliseconds, the red LED every 500 milliseconds, the green LED every 250 milliseconds, and the blue LED every 125 milliseconds. Since these values will not change throughout the program, we begin with the const keyword to define them as constant, ensuring that they remain fixed during execution. The integer data type is sufficient for storing delay values because the specified delays fall well within the range of an integer. White delay equals 2000 sets the white LED to toggle every 2000 milliseconds. Yellow delay equals 1000 sets the yellow LED to toggle every 1000 milliseconds. Red delay equals 500. Green delay equals 250. And blue delay equals 125. In this way, we have defined the variables that determine the time intervals in milliseconds for the LEDs to blink. Now, we are reaching the final stage of defining the variables. The variables we will define now will store how many times each LED lights up in the program. This information may not necessarily be shown to the user. However, for verification purposes and to determine how accurately the program is functioning, printing these values on the screen displaying how many times each LED operates in the program will be beneficial. For this, we will store the values in variables of the integer type. Since the values of these variables will change, we do not define them as constants. Let's name our variables as white count. Since these LEDs will not operate initially, it is beneficial to define the initial values of these variables as 0. In this way, we will define separate variables to store the count of operations for each LED, and we will set their initial values to 0. These variables count how many times each LED has toggled to the on state. For example, blue count will increase by 1 every time the blue LED turns on. This block helps us track the activity of each LED, which will be displayed in the serial monitor later. The variable definitions are now complete. We continue writing our commands using the setup block. In this part, we will write the configuration commands to specify which pin of the Arduino board will be used for which purpose. For this, we use the pin mode statement to specify the purpose for which each pin will be used. We set the pin associated with the white variable as an output pin. This means that the pin will provide power to an external component, in this case, an LED. The pin will send voltage to control the LED state on or off. Similar to the previous line, we will set the pin connected to the yellow variable as an output pin. This will also control an LED, and the pin will send a signal to either turn the LED on or off. Next, we will set the pin corresponding to the red variable to output mode. The pin will be responsible for controlling the red LED. And we will set the pin associated with the green variable as an output pin to control the green LED. Lastly, we will define the pin for the blue variable as an output. It will control the blue LED in the same way as the other pins. The pin mode function is essential for configuring the pins, specifying whether they should send data or receive data. In this case, each pin is being set as an output to drive the LEDs. Then by the serial begin command, we will initialize the serial communication with a baud rate of 9600 bits per second. It's typically used for debugging or sending data to and from the computer via the serial monitor. Now, we move on to the next phase, which is the loop block. This is where we write the commands that will run continuously in the program. Here, we will control the LEDs, adjust their behavior, and include any other functionality that needs to happen in a repetitive cycle. First, we will write the previously defined variable called current time, which will store the duration for which the Arduino board has been running. The value of this variable will be assigned to the value returned by the millis function. In this way, the variable will store how long the board has been running since it was powered on. We start controlling the LEDs with the millis function, beginning with the white LED connected to pin number 2, and I'm adding a comment line here. The commands we will write below are the ones required to control the operation of this LED. We will check whether the elapsed time since the last toggle of the white LED has reached or exceeded the predefined delay set by the white delay variable. Current time minus white time calculates the time that has passed since the last recorded toggle for the white LED. If the result is greater than or equal to the value of the white delay variable, the if block here will execute, and the commands under the if block will be carried out. In other words, the delay time for the white LED is set to 2000. When the difference between the current time and the last time the white LED state changed is 2000 or greater, the if block will execute. And with the commands we will write in this if block, if the white LED is currently on, it will turn off, or if it is off, it will be turned on. If the condition is true, we will update the white time variable to the current time. This marks the exact moment the LED state was toggled. Resetting white time ensures that the elapsed time for the next blink is calculated starting from this moment. Accurate updates are critical here, as failing to reset this variable would cause the LED to toggle incorrectly or inconsistently. Then we will check whether the white LED is currently off. With the digital read command, we read data from a digital pin, and within the parentheses, we specify which pin we want to read data from. The white variable was storing the value of pin number 2. If the value we read from here is low, meaning the white LED connected to pin number 2 is not lit at that moment, the commands within the if block will execute. If this condition is met, meaning pin number 2 is in the off state, we will use the digital write command under the if block to turn it on. After the digital write command, the parentheses contain the pin represented by the white variable, followed by the value we want to set for that pin, which can be either high or low. By writing the high expression here, we ensure that the white LED, which is in the off state, will turn on. Here, instead of using low, you could write 0, and instead of high, you could write 1 to represent the off and on states, respectively. Both will work the same way in terms of functionality. Next, we increment the value of the white count variable, which we defined earlier, by 1. This will keep track of how many times the white LED has been turned on. We will print these values to the screen at the end of the program. When the if block doesn't execute, the else block will run. This means that if pin number 2 is not in the low state but is instead in the high state, indicating that the white LED is currently on, then we will ensure that the LED is turned off. To achieve this, we use the digital write command to send a low value to pin number 2. And in this way, if this LED is on, it will turn off. Using the millis function, we made the white LED change its state every 2000 milliseconds. Similarly, we will write the same command blocks for the yellow, red, green, and blue LEDs. In this section, we use the variables related to the state of the white LED. For the other LEDs, the only difference will be to ensure that we use the variable names we defined for each color in the appropriate places. We have also completed the code for the yellow LED. At this stage, we compile our program. This step is necessary because we have defined quite a large number of variables. There might be errors in the code, so we occasionally compile the program to identify and fix any mistakes. As you can see, there are no errors in our program. We will organize the necessary commands for the red LED with a similar command algorithm. We have completed writing the command sequences that will make the LEDs blink at specific intervals using the millis function. Now, let's print on the screen how many times each LED has been activated. We will use the serial print line command to do this. Inside the parentheses, we will write string current time. This converts the current time in milliseconds into a string format so that we can print it. We want to display this value so that we know exactly when each LED change happens in the program. If we don't use the string function, the program would not be able to properly concatenate the current time, which is an unsigned long, with the other string components in the serial print line function. Next, we concatenate additional information to the string. The plus symbol is used to join these pieces of data together. Each piece will appear in the output as a single message. We will add a space inside the quotation marks so that the phrases don't get written together and the text becomes more readable. We will write white and then add another plus sign. And we will also convert the white count variable to a string and print it, as it is an integer type variable. So the string white count function converts the white count variable, which keeps track of how many times the white LED has toggled, into a string and appends it to the message. Similarly, we do this for the other colors yellow, red, green, and blue. For each color, we print the corresponding LED count. With this, we have finished the command writing process. Let's test if there are any errors in our commands by compiling the program. As you can see, there are no errors. You are now viewing the entire code of our project. In the first line of commands, we defined variables that indicate which LED is connected to which pin on the Arduino Uno board. In the second line, we created an unsigned long variable named current time, which will store the operating time of the Arduino Uno board. In the next line, we defined additional unsigned long variables that will store the state change times for their respective LEDs. By state change, we mean the transition of the LED from being on to off or from off to on. In the fourth line, we declared constant integer variables whose values are fixed and cannot be changed during the program's execution. These variables specify the delay intervals in milliseconds at which the state of each LED will change. In the final line related to variable declarations, we defined integer variables that will keep track of how many times each LED has turned on. It is important to note that these variables only count the number of times the LEDs light up. They do not track when the LEDs turn off. Moving on to the setup block, we use the pin mode command to define the pins connected to the LEDs as outputs. Additionally, we initialize serial communication at a baud rate of 9600 to ensure that data is transmitted to the serial monitor accurately and efficiently. Finally, in the loop block, we began by assigning the value of the Arduino's runtime, obtained from the millis function, to the current time variable. The first set of commands in this block relates to the control of the white LED. In the conditional statement of the if structure, we subtract the white time from the current time. The current time represents the runtime of the Arduino Uno board, while the white time stores the exact time of the last state change of the white LED in milliseconds. If the difference between these two values is greater than or equal to the white delay, which is the predefined interval in milliseconds at which the state of the white LED is supposed to change, then the if block will execute. In our case, white delay is set to 2000 milliseconds. This means that whenever the Arduino Uno board has been running for at least 2000 milliseconds since the last state change of the white LED, or if exactly 2000 milliseconds have passed, the conditions inside the if block will be triggered. For example, when the Arduino board is first powered on and current time reaches 2000 milliseconds, the condition will be true and the code inside the block will execute. Similarly, every subsequent 2000 millisecond interval will trigger this block. You might wonder why we use a greater than or equal to condition instead of just equal to. This happens because the millis function operates very quickly and there's a chance of missing specific values due to the rapid progression of time within the program. For example, the current time value might jump directly from 1999 to 2001, completely skipping the value of 2000. By including the greater than operator, we ensure that the program accounts for such situations, effectively preventing any potential data loss or missed triggers. While it's unlikely to cause an issue in every scenario, adding this safeguard ensures the program operates reliably. Then, inside this if block, we need to update the last recorded state change time of the white LED. To do this, we assign the current runtime value stored in current time to the white time. In other words, the last time the white LED state changed is now. This ensures that the program correctly tracks when the LED last toggled and prepares for the next cycle. Now, we can proceed to implement the state change of the white LED. This means if the LED is currently off, we will turn it on, or if it's already on, we'll turn it off. To achieve this, we need to read the LED's current state from its respective digital pin. We use an if statement combined with the digital read function. This function allows us to read the digital state of the pin associated with the white LED. Earlier in the code, we defined the white variable as 2, representing the pin number. So here, we are asking the program to read the digital state of pin 2 on the Arduino Uno. If the value read from the pin is equal to low, this means the LED is currently off. In this case, we use the digital write function to set the pin to high, which turns the LED on. Since the LED has now turned on, we increment the white count variable by 1 using the ++ operator. This keeps track of how many times the white LED has been turned on. If the if condition is not met, meaning if digital read white equals low returns false, then this indicates that the LED is already on. In this scenario, the program executes the else block where we use digital write white low to turn the LED off. The same structure and logic are applied to the yellow, red, green, and blue LEDs. They all follow the same approach. At the end of the loop block, we use the serial print line function to print all the relevant data to the serial monitor. This serves as a way to verify and validate the program's operation. First, we display the value of the current time, which represents how long the Arduino board has been running in milliseconds. Then, we sequentially display how many times each LED has turned on. This output acts as a form of debugging or program verification, helping us ensure everything is functioning as intended. Now, here's an interesting observation about the LED's behavior. Each LED will toggle its state at a rate that is twice as fast as the one before it. For example, if the white LED has turned on 10 times, the yellow LED will have turned on 20 times, the red LED 40 times, the green LED 80 times, and the blue LED 160 times. This is because the delay intervals between state changes for each LED are halved in sequence. To clarify further, the white LED toggles its state every 2000 milliseconds, while the yellow LED toggles every 1000 milliseconds. Since the yellow LED toggles twice as fast as the white LED, it will naturally turn on twice as many times over the same period. Coding this project is far from simple. It requires a well-thought-out algorithm and careful attention to detail. So, if you find yourself struggling while trying to implement this program on your own, know that this is perfectly normal for a program of this complexity. To make the learning process more effective, compare the code you write with the explanation and the sample code provided here. Now it's time to test our project. We've connected the Arduino to the computer via USB, and from the Tools menu, we select Serial Monitor. After this, we upload our code to the Arduino board. Once the code is successfully uploaded to the Arduino, we switch to the Serial Monitor tab. As you can see, our project is working perfectly. The white LED changes state every 2000 milliseconds, the yellow LED every 1000 milliseconds, the red LED every 500 milliseconds, the green LED every 250 milliseconds, and the blue LED every 125 milliseconds. These intervals were specified earlier in our code using constants, which tell the program exactly how long to wait before toggling the state of each LED. When we examine the data on the serial monitor, we see the running time of the Arduino Uno displayed first, followed by the number of times each LED has turned on. We observe that each LED has turned on twice as many times as the one before it. For example, if the white LED turned on 10 times, the yellow LED should have turned on 20 times, and so on. This pattern follows because the LEDs are set to change state at intervals that are halving for each subsequent LED. At this point, we disconnect the Arduino Uno from the USB cable to examine the results further. The process happens quickly, and it might be challenging to capture these changes in real time. So when we disconnect the Arduino, it's easier to find a specific line of data where the values are more clearly visible for analysis. The number of times each LED is toggled is printed line by line, so we can easily track the behavior of our LEDs and confirm that everything is functioning as expected. With that, we've successfully completed the testing phase of our project. We've verified that the program works as intended, and the LEDs are changing states at the correct intervals based on the timings we set. Before we finish, feel free to share your thoughts and feedback about this video in the comments. If you have any questions or if something wasn't clear, drop them in the comments below. I'll do my best to answer and help you out. Don't forget to like this video and subscribe to the channel for more content like this. Thanks for watching, and see you in the next video.